Hi, today I'm going to give an explanation about the Python program that I wrote titled Conic Section Generator. Now, as the name suggests, the program will allow the user to enter in 5 points and generate the equation of the conic that passes through those 5 points. So let's take a look. And this is the graphic user interface for the program. So please enter 5 distinct points, point 1 until point 5. And since these points are already initialized, we might as well just press the generate conic button and the equation will be displayed below. So generate conic, then conic section through 5 points. The graph is also shown. So since these 5 points are collinear, then it's no surprise that it's just one straight line and the line is y equals to x. Or negative x plus y equals 0. Same thing, right? But we can also change stuff a bit, like let's say 0 to negative 2 to 3, negative 3. And maybe generate conic. And as you can see, since these points are no longer collinear, we have coincidentally, it's a hyperbola passing through those 5 points. How about we change stuff again, maybe negative 1 to 0.4, generate conic, and it's another hyperbola. With the equation is shown below. But another more interesting feature of this program is that it enables us to use input operations inside the entries. So as you can see on the right hand side, we can perform operations like, let's say 2 plus 3. This will give us a 5. And we can also use mathematical constants like 1 divided by 2 times e. This also works. Or functions such as maybe cosine of pi in radians. So this will be negative 1. Let's generate the conic. And it's another hyperbola. Okay. But another thing is that since e is a transcendental number with an infinite number of decimal places, the equation at the bottom is kind of messy. I'm just showing 3 decimal places, but it's really messy. So if we don't want that, we can change the number of maximum decimal places shown. So let's say we want it to be just integers, max number of decimal places 0, and I don't want a graph. Okay, no graph. Generate conic, you can see it's the exact same equation except that all the coefficients, they are rounded to the nearest integer. One more interesting feature is that let's say I have 1, 2, 2, 3, 3. So basically I want the collinear points again, 4, 4, 5, 5. So this, show the graph, it's just a straight line, nothing special. But if I change this so that 4 points are collinear and just 1 point is not collinear with the other points, and I generate the conic, the line will pass through these 4 points, but there will be no line passing through this point. However, shown here will be the equation is negative x plus y equals to 0, union any line through this outlier point, which is 3, 4. Because the line can be of any angle as long as it passes through this point. I didn't show it in the graph, but because it's not unique, but any line through 3, 4 will satisfy the conditions. Finally, I've also included input validation into the program. So if we enter something illegal, like let's say e is defined, so e is fine. But if I enter 2 times a, then the program will detect it and the box will turn red, telling me that there's an error and I can't generate the conic anymore. If I change this back, it works. Same for stuff like, let's say, the natural log of negative 2. It is not defined, log of negative 2, so it doesn't work. I can't generate the conic, but log of 2 works. And also we need 5 distinct points to define a conic. So if the points are not distinct, it makes things very difficult. And 1, negative 1, 1, 1, 1, 1, it doesn't work. Points must be distinct. So change it back, then it works. Generate the conic. Okay. Okay, this graph isn't very nice because I used the SymPy plotting to plot this graph, so it has some rendering issues when the points are too close together, but this is probably this should be two intersecting lines. Yeah, it should be two intersecting lines with this equation. So now we are done with the interface of the program, and let's move on to the code and see how this program actually works. We have moved on to the code here. Oops, main open with right. Okay, so there's quite a lot of code for this program, and most of the code isn't actually related to the math. It's just some technical stuff like where the buttons go, what color should things be. So I'm not going to explain about those things, and I'm going to focus mainly on the math involved behind this program. So let's start. Since this is written in Python, there will be a lot of library functions. It's very helpful. And we have our global constants defined here, pi, e, and phi. Then the perhaps more interesting is the class conic over here. So this class generates the equation of the conic, stores the information, and plots the graph. Since we have everything is happening in R2, the xy plane, so we will have the symbolic variables x and y. After that, we also need the points to generate the conic. So this point list, it will get and store the points that the user input in the entries. There are 5 entries, so there will be 5. The loop will go 5 times to get the point list. Then we need also to find how many points are collinear and the outlier point. Remember that there was one example I showed where the 4 points were collinear but 1 point was not on the line. So we need to account for that as well, because otherwise we'll get an error. After that, we generate the matrix corresponding to the determinant equation, which we will set equals to 0. This is the general way how we get the equation of the conic. Then we need to get the equation of the conic itself. Using this, I'll explain more on this later. And since I'm using a graphic user interface, then the formatting, everything will have to be done manually. So this will be the stuff related to formatting. And if the user wants to display a graph, then show the graph on screen. So let's move on to our first function, check collinear, to see how many collinear points are there. First, we need to iterate through every pair of points. There are 5 points, so we need to go 5c 2 times, 5 choose 2 times, and we generate a vector from point 1, the first point, to the second point. So this will be our vectors. And we need to iterate through every vector and check if those two vectors are parallel using the cross product. Because if they are parallel, it means that since there are two vectors, so the 3 points corresponding to the two vectors will be on the same straight line. We have count equals to 0. Then we go a loop and we use the cross product, cross the first vector with the second vector, and check if it's equals to 0. If it is equals to 0, then that means they are collinear, so count plus 1. And a concern that you might have is that the vectors are in R2, so the cross product is only defined in R3. But this program, this numpy function handles it, and it automatically makes the ijk, the kth coefficient, to be 0, so things still work out. And since we are going through every vector, there might be, if we accidentally pick a vector with a initial point starting from the outlier point, then naturally the cross product of all the vectors will not be 0. So we need to take into account of that, and we make sure that we set the number of collinear points equals to the largest of those counts through each iteration. So our collinear count will be the max of the collinear number plus 1. And if there are 4 collinear points, then the outlier will be defined as the point that is not on the line. So the outlier will be the index of the point list that has the lowest collinear number. And we will return the number of collinear points and the outlier point back to the class. Then with that in mind, we need to extract. That means we need to convert the input points into a matrix, and this is the first row of the matrix: x squared, xy, xy squared, xy, 1. Then we need 5 more rows because this is a 6 by 6 matrix. We only have the first row. So get the coordinates and x squared, xy, y squared, and so on. Then we append this thing to the back of this thing. So after 5 iterations, we will have a very long list, which using NumPy, I'll reshape it to become a 6 by 6 matrix and return it to the class. Then we need to get our actual equation. So these are our variables, and we'll start by saying that if there are less than 4 collinear points, then we use the normal method to get the determinant and stuff. But if there are 4 or more collinear points, then we'll get that the determinant is equals to 0 because the conic section is not unique. So we need to use another method. Anyway, we'll see the first case first. If collinear count is less than 4, then the coefficient of each term will be using column row expansion. I'll find the coefficient. Actually, I can just find the determinant directly, but I think it's more convenient if I get the coefficients first because I want to do some useful stuff with it. So column row expansion, then this will be the coefficients. But if there are 4 or more collinear points, then I'll need to use another function that I'll explain later. So we just keep that in mind first. Assume that we already have the coefficients. Now I don't like floating point errors because let's say you enter in 2 and the program prints out 2.000000001. So that's very annoying. So if the absolute value of the value minus the rounded value is less than 1 times 10 to the negative 10, then I might as well just print the integer value. Then if all the coefficients are integers and they have a common factor, like let's say we get the equation is 2x squared plus 2 equals to 0. We might as well just divide it by 2 to get x squared plus 1 equals to 0. So divide everything by their greatest common divisor to simplify the equation. Then now we have a very neat set of coefficients that we can assemble the equation with. So just for I in range 6, that means we iterate through the coefficients, and the equation will be the coefficient of the variable times the variable. So these are the variables. Then we return the coefficient and the equation. After that, remember that previously we said that we needed this to be less than 4 collinear points. So if there are 4 or more collinear points, then we need to use the getLine method, which is over here. So this getLine method will take the points, all the points except the outlier, which means that all those points inside this list will be those that are collinear because we excluded the outlier. Then we need to find the gradient of this line, and it doesn't really matter which point we use since they are all collinear. So we use the point slope form to get the equation. Gradient equals to y1 minus y0 over x1 minus x0. And we use y minus y0 equals to mx minus x0, return this equation. However, if the gradient is infinite, then it must be a vertical line. So if it's m, is this thing over here is equals to 0, then we get a 0 division error because it's a vertical line. So we return x minus x0 equals to 0. Now because I'm using a graphic user interface, so I need to format the equation. There's really a lot of annoying stuff. So this print equation, this function will handle all the annoying stuff. For example, like let's say the coefficient is 1. Let's say maybe x squared plus y equals to 0. So y, the coefficient of y equals to 1. So I don't print x squared plus 1y equals to 0. I just print x squared plus y equals to 0. But the program doesn't know that, so I have to handle all the cases. Yeah, basically that's about it. There's nothing very interesting here except all these many cases. And perhaps this is something I should point out, that if there are 4 collinear points, then like the example I showed previously, I will have to print the equation union with any line through that outlier point. So after that, I'll display the equation on the GUI and to show the user what the equation is. So this method graphs the conic on the screen. So because the conic, ideally I want to show all the points on the graph. If, let's say, all 4 points are very close to the origin, but I have one point that is, let's say, 1000, 1000, very far away. So it won't be shown in the graph, and that's not really nice. So I want to determine how large the graph must be. It means I find a minimum x value, maximum x value, y min and y max, and I find the range so that I know how big my graph should be. Then using the SymPy plotting tool, I plot the implicit function with the equation of the conic and my range. So this is my range, x range, y range, and it's nice to have the axis center as the origin so that it gives a better perspective of what the conic actually is. But this is just the equation of the conic. Ideally we also want to see the points on the graph. So there's no built-in point plotting tool in SymPy, so I have to do this manually by marking an X. This is done by using 2 line segments intersecting at each point. So I do this getting the equation in point slope form. Let's say x0 and y0 is the point I want to graph. So I'll use the point slope form, y minus y0 equals to mx minus x0, and I plot it there using a very short line segment, and I also set the gradient to be 1 to simplify the calculation. So then after that, show the graph. So the next class that we want to talk about is the input class, but there's actually nothing really special about here because there's just the input, right, the boxes that you write stuff in, and there's not much math related here, it's just technical stuff, so I won't go in here. So this parse basically checks to see if the input is valid. Like just now, if you key in 2 times E, it works because E is defined, but 2 times A doesn't work because A is not defined. Or if the user tries to enter plot the point ABC, 1 minus 2, ABC is not defined, so this will throw an error and ask the user to re-enter. The validate method makes sure that the points are unique, because again, if the points are not unique, then they don't define a unique conic. So again, there's not much here. It's just that if the points are unique, then fine. If it's not unique, then you'll change the background entry to become red color, and the user can't press the generate conic button anymore. Validate toggle is similar, except that it works for the number of decimal places to show. Remember that there was a box at the bottom right. So this one makes sure that the user doesn't ask the program to enter, like, let's say, show me 1.7 decimal places. That doesn't make sense. Change status changes the status of the graph, so that if the user wants to press show me the graph, then yes. If they press again, then don't show me the graph, so it shows no. And this is just something that I use to convert the program to exe, some technical stuff. And this part, beginning from this part, is just the graphic user interface. So like, let's say, where is the button, how high should be the text be, how big should the text be, what color should this thing be. So there's nothing interesting over here. It's just, yeah. So that should be all for my program, and I hope you like it, and thank you for watching. Thanks.